This will be a quick presentation on doing some calculations with thermal radiation for objects. And just for a reminder, for thermal radiation, often objects, particularly things out in space, will produce nice smooth curves for the radiation that they give off. And if we graph the intensity, and I'm just going to use the letter I for intensity, it's usually measured in watts per square meter, and a watt is a unit of power. And then you graph lambda, the wavelength on the horizontal axis, and lambda can be measured in meters, nanometers, all sorts of different units, but I'll just put nanometers on here. And you should know that anytime you see that lowercase n in front of another unit, you just replace it with times 10 to the minus ninth. So it's just going to be a number. And the thermal radiation curve for a perfect emitter is a nice smooth curve. The variations from that nice smooth curve can also tell us information about the object, but that's what it might look like. This wavelength right here, which is sometimes called lambda max, it's also sometimes called lambda peak. It's the same thing. It's the wavelength of where that curve is at its highest, and it depends on the temperature. And the relation that describes the relation between temperature and lambda max is called Wien's law. And if you measure the wavelength in meters, Wien's law is lambda max times T equals 2.898 times 10 to the minus third Kelvin meters. If you measure the wavelength in nanometers, it looks only a little different. You have to do a little unit conversion on this particular number, but it'll be 2.898 times 10 to the sixth Kelvin nanometers. And there's a factor of 1,000,000,000 between a meter and a nanometer, and that's why there's a factor of 1,000,000,000 between those two things. You won't have to memorize this value. I always give people that if they have to do anything with this. But that's the way it works. Now let's just do a quick example problem. An object has a temperature of 5,280 Kelvin. At what wavelength does it emit the most radiation? Well, we can solve our equation here. Lambda max is going to equal that constant 2.898 times 10 to the sixth, and I'll use the Kelvin nanometer version of it, divided by the temperature, which in this case is 5,280 Kelvin. And we just pop the numbers into the calculator. And I get about lambda max is equal to, I've got 3 significant figures here, I'll keep 3 significant here, 549 nanometers, which is just about right in the middle of the visible spectrum, which goes from 400 nanometers approximately up to about 700 nanometers. Now, something we can say from this, if we solve it in terms of just the variables again, is that lambda max is equal to 2.898 times 10 to the sixth Kelvin nanometers divided by the temperature. And we would say in words, the wavelength of maximum intensity is inversely proportional to the temperature. And in an inverse proportion, the thing it's proportional to goes on the bottom of a fraction. And on the bottom of a fraction, the bigger you make this number, the smaller this will be. So the higher the temperature, the shorter the wavelength of maximum intensity. The lower the temperature, the longer the wavelength of maximum intensity. So that's a verbal way of understanding it. Hotter things have shorter wavelengths of maximum intensity. Turns out they have higher frequencies of maximum intensity, but we usually use wavelength in astronomy classes when we're using this. So that's a way that you can remember that. Going the other direction, okay, an object in space is being studied by astronomers. They find that the wavelength at which it emits the most radiation is 957 nanometers. What is its temperature? Well, we can do that. Since lambda max times T is equal to that constant, and I'll write it on the next step, the T is going to equal the constant divided by lambda max. So we can go two ways on this. If we know the temperature of an object, we can figure out the wavelength at which it will emit the most radiation. If we know the wavelength at which it emits the most radiation, which we get by observation, we can figure out its temperature. This is how we measure the temperature of objects out in space. So 2.898 times 10 to the 6th Kelvin nanometers, and I'm using nanometers here because that's the wavelength at which, or the meter units that they use for figuring out the wavelength of maximum intensity, divide by 957 nanometers, which by the way is in the near infrared part of the spectrum. It's beyond the red end of our spectrum at 700 nanometers, so that puts it into the infrared. And this would have a temperature of about 3030 Kelvin. So quite a bit lower than the surface temperature of our sun, which is about 5800 Kelvin or so. So a little bit cooler of an object. So you can use Wien's law and go either direction. We said earlier that the wavelength of maximum intensity is inversely proportional to the temperature. We can also say that the temperature is inversely proportional to the wavelength of maximum intensity. So the higher the wavelength of maximum intensity, the lower the temperature is going to be. And those two things work in concert. Okay, there's another law of electromagnetic radiation that we can figure out, or that we can study on here. And this will have to do with looking at, instead of just a single wavelength on this curve, it'll consider all the wavelengths of light. And so we've got the intensity here and the wavelength here, and we get this thermal radiation curve that looks like that. It's not a perfect bell curve. It's got a tail going out to the right that goes very far. But if we calculate the entire area under this curve, it turns out you get something called the energy flux, or the radiant emittance. It's the total electromagnetic radiation given off by the object, considering all wavelengths. And this goes under something called the Stefan Boltzmann Law. These were two different people here. It's sometimes just letter F for flux, or the radiant emittance, depending on which book you happen to look in. But it turns out that that total energy given off by that is equal to another constant times the temperature to the 4th power. This constant that's a lowercase Greek letter sigma, and it just stands for a number. And sigma, we're not ever going to do calculations where we actually use this, but we do use this to compare things. And sigma is equal to about 5.67 times 10 to the minus 8th, and it's watts per meter squared, Kelvin to the minus 4th. And that way, when you multiply sigma times the temperature to the 4th power, you'll end up with watts per meter squared, and it'll give you the total value under here. But the important thing about this is it goes with the 4th power of the temperature. That means hotter objects give off enormously more electromagnetic radiation. For instance, if you compare two things, let's suppose the temperature of our cool object, and I'm going to put cool in parentheses here, is equal to 4,200 Kelvin, and the temperature of our hot object, surface temperature in every case, is 5,800 Kelvin. Now, these two temperatures happen to be the surface temperature of two stars that are fairly well known. This one is roughly the surface temperature of our sun. This temperature is the surface temperature of the star Arcturus, which is one of the, I think it's actually the third brightest individual star in the sky. And we can compare, see how much more radiation our sun gives off per square meter of surface than Arcturus. Okay, so here's Arcturus, and here's our sun. And I would just, for comparison, I would go F for the sun divided by F for Arcturus. I'll just call it arc, and it's going to be 5,800 Kelvin to the 4th divided by 4,200 Kelvin to the 4th. And the kelvins will divide out, and I'll just have a pure number. And it turns out that this ends up being about 3.6. And what that means is that every square meter of surface on the sun gives off 3.6 times as much energy as every square meter on Arcturus. Now, it turns out Arcturus is a much larger star than the sun, diameter-wise, and so it actually has a larger surface area, but still, the hotter the object, the more radiation it gives off per square meter of surface. Let's suppose one star is 5 times as hot as another, which can happen. So let's just plug that in. Star A Okay, star A has a surface temperature 5 times as high as that of star B. How many times more is the flux from star A compared to star B? Now again, the flux is the total amount of energy given off per square meter of surface. Well, the temperature of star A is equal to 5 times the temperature of star B. So if I was just comparing these things, I would take the flux for A and divide it by the flux for B. Okay, now flux for A is going to be sigma T sub A to the 4th. That for B is going to be sigma T sub B for the 4th. But if I'm just comparing them by ratio, the sigmas divide out, and all that's going to matter here is T sub A is 5T sub B. So I have to take this thing and the 5 gets raised to the 4th power as well, and then I've got t sub b to the 4th power here. Well, the t sub b's are going to end up dividing out. When you've got two things multiplied together in parentheses, you'll raise the 5 to the 4th power and the t sub b to the 4th power, and so you'll get 5 to the 4th t sub b to the 4th over t sub b to the 4th, and you can see those temperatures divide out, and all that's left is the 5 to the 4th. Okay, I was going to put an exclamation mark there, but I don't want you to confuse it with a factorial, which is a different mathematical operation. But what this means is every square meter of star A is going to give off 625 times as much energy as every square meter of star B. And that's an amazing number, but that's the way things depend on temperature.